what we discussed now should be familiar to most of you, and so it should be familiar to all of you, and I do it very briefly. So we have the notion of germs of function at a point, and this is an equivalence class of function defined the neighborhood of this point, and germ is nevet בעברית, and the collection of all such form a ring called the scope of all, and this ring changes to from point to point, of course, but since being analytic is something that we express in local coordinates, or maybe before making the observation, let's give one last definition. We define mx inside ox to be the subset a priori of functions or germs of functions, fine, germs that vanish at x. No observation.
There's a reason why you keep indenting yourself into the. I'm just joking.
Yeah, no, there is no reason. But I mean, there must be a reason. Clearly,
He's hoping that it takes to answer. It's
an
an
ideal.
ideal language.
Yeah,
It's a continuation of the previous line.
Is an ideal. So I start something here and then it's just keep going here. When I was a student here, Kachalski would start making a small remark here and write it here, then the whole class would be going. And arranging something. And so the observation I want to make, since I can express everything in local coordinates, then all these OXs are just the same. And there is a universal guy. OX is the same as some O, and this is a subring of KX. And this is the collection of formal power series which converge in some polys. Right, so this is a universal guy, and they all look alike by not canonically, by a choice, by any choice of local coordinates of the chart. And this clearly has an ideal in it, and is defined. If you want the O intersection is okay. So under verification, OX is O, I have MX is the same as M. And now I want to claim that all those guys are local fields, and MX is the unique maximal ideal in OX. Claim. MX is the unique maximal ideal in OX. And in order to do so, is enough so we can write every function, every formal power series. I mean, this way of writing is actually is valid here. Every formal power series I can write as an element of this one and a constant formal power series. And I'm carrying it here. This is a K model, or K vector space.
Okay,
This is a K linear.
this
This is constant. This is the embedding of K linears of the constants. It's just a remark. Now, the claim is, okay, this is a remark, I'm not using it right now, but the claim, what is this claim? That M is a unique maximal ideal. It's the same as saying that every element which is not there is invertible. Actually, we've seen, and this is most trigger, okay. This is not what we've seen. Okay. It is, I would say, so it is rather easy to invert every element as a formal power series, every element which is not in M. Invertibility now is not about composition, it's about pointwise multiplication, right? Or multiplication of formal power series. It is rather easy to see that every element is invertible as a formal power series, every element which has a non-zero constant term. What's maybe is less obvious is that this inverse, if a function, if a formal power series f converges, then the inverse converges as well. And this is what we see. Need to show if f is in O minus n, f analytic, basically, and f0 is not zero, then f minus 1 exists and analytic. Up to normalization, I can assume that f0 is 1. And I can write f as 1 minus g when g is 0. Now, take another function, h. And h will be sum of x to the I. This is an analytic function at 0, right? No problem. And actually, it's it behaves as this guy. This is analytic at 0. And it follows, since f is analytic at 0, g is analytic, and h is analytic, then h composed g is analytic at 0. But what is this? So this is 1 over 1 minus g, which is 1 over. So every element which is not in my ideal is invertible, and I prove that this ideal is maximal, a unique maximal ideal, and for O, and same goes for all of these. I'll put another definition on the board. For an element in O, it is very easy for me to define its order of 0. What is the degree of a minimal non-positive coefficient? What is the minimal degree of a non-positive coefficient? So we define
non-positive and non-zero.
n such that f is not in m to the n. These are power of this mathematical and well, maybe I will not write it down, but for any function which is defined at a neighborhood of x, I can regard it as a germ at x and consider its order of 0. Order is 0 of f at x. Now, the definition of the time space we define, as usual, we define first the cotangent space to be mx also mx squared. Cotangent space of x at x. So this should be like 3 volts. We define dx to be the dual of the cotangent. Of x at x. As usual, and I'll repeat this in a second, we have an identification of the tangent space at x with the derivation. A derivation on OX is a linear map, or linear functional, a linear, satisfying if I have two functions, f and g, two German functions, then dfg are usually, so df is a scalar, right? Times, here's another scalar, g at 0, or g at x. And I can do the other round. Everything is commutative, so I could have written it otherwise as well, but sometimes we look at non-commutative derivations, so it makes some sense to view this way. Claim so I should say again, I assume that most of you have seen it in differential geometry or somewhere, and derivation is, if you think about real manifolds, etc., derivation are just directional derivatives at the point. So this is really how we think most of the time as a tangent space, and this is what the claim says. There is a natural identification. X with all the derivation over k from OX to k. And you understand what I mean by this? It's the space of all derivations. Two lines, and I should explain given a derivation how to construct a functional on, well, for D, I should give you an element here. That is I should give you a functional on that guy. So I should give you a functional on this that vanishes on that. So first of all, let me give you that. Well, D is a function on OX, so it's a function on M as well. And if I have what is this? This is the elements here are not necessarily product of guys in M. They are generally this is spanned by products of guys in M. But I'm k-linear, so it's enough to check on this generating set. So if I have a product, F and G, both F and G are in M, so D of F times G, so this is a typical generators of M squared, will be whatever that is times 0 because G is in M, plus 0 times whatever. So D restricted. Given D in there, vanish on M square, hence define an element in which is a time space. Now, given element here, so if I do have now given now phi in Tx, which is so maybe I guess I'm identifying this with uniquely identified with the annihilator and the value of M square in M star, right? And do this with again. So if I have phi now, then I get an element in M star that vanishes on M square, and but I want an element defined everywhere, so we extend it as 0 here. Phi could be extended to O, which is mx. Okay. Check. This will so again, instead of reading this equation for derivations of k-linear functions on OX, which have the following two properties. Okay. If I have a derivation, what to give to 1? Well, d of 1 times 1 should be d of 1 times 1 plus 1 times d of 1. So this 1 should be 0. And okay, this is the okay, so now I'm not sure I'll use it that much, but this is something that you should know. So far I have given an analytic manifold X. I'm having at each point a tangent space to that point, which I can identify with the space of derivations at this point. And I want to make the following observation. Observe. If I have X go y, if I have some phi here, X goes to phi x, then I guess I have this, I'm getting this map if I have a function at y defined in the neighborhood of phi x, then I can put it back or recompose it with phi to get a function here. If this function vanishes at the point and I compose it with phi, it will vanish at x. If I have a product of two sets, I compose with phi. So I guess that I'm getting such a thing, and hence I'm getting a dual map. Maybe this is phi bar. But of course I don't call it, I call it b phi x. Similarly, I may think about it as a derivation. If I have a derivation on that, I can recompose it with this map and get a derivation of that. So it's same identification. I mean, time estimation. Okay, so next thing I want to do is state an IFT for manifolds. No new math, just if is local isomorphism at x, then of course d phi of f is in GL. Oh, d phi of x, sorry. Then the unit is a linear isomorphism, and the IFT same, the converse. Okay? And this is clearly not a coordinate, this is what we call course, in local coordinates, I do identify these two spaces, and claiming that the phi is actually an invertible operator. If someone likes French, and we say that phi is Italy at x, and phi is a tal if it is a tal at every point. No, and this is an isomorphism. Oh, sorry. So it's a covering map. It's an anonymous problem. It's a local normalization. We should have in mind. I mean, for real manifold, we're talking about covering maps. Now, question is, how much time do I actually have? Let's take this corollary. If I have u here, okay, then F defines a coordinate system at x if and only if the FIs, F is just a map, right? At x. And this collection I values for a basis. Okay. To say that it forms a basis, to say that the matrix I'm getting is an what? Maybe.
If I.
Sorry?
What do you mean?
What is the question?
Fi is what? Is F composed with?
No, F is a bunch of I's. Oh, yeah, I mean, the FIs are F composed with the projection along the coordinates. I'm actually thinking about, for functions into Kn, I'm thinking this way. I think about them as tuples. According to my convention, now we should think of F as an absolute function. Oh, whatever. Yes, the Fi is F composed with the coordinate projection. Okay. Is this clear? What? Okay.
So
thank you.
dfi at x is, where does it leave the coordinate formula?
You're basically taking this natural
It lives in a
isomorphism to K and T.
Oh, I guess it's clear. Wow.
but if fi is a map actually to k, then dfi is a map from the tangent space.
It's for a basis to
Each dfi at x is a vector, tangent vector to k at 0. Right? Because fi is, the image of fi is k.
Yes.
So somehow that's what confuses me.
But once you have basis, it
so that are here or in the do of that, right?
Here.
Here. This is very confusing, right? Space is isomorphic, so. And
And you have a natural isomorphism between this one and KN.
Not natural. So
Well,
I
now,
don't understand
KN
why
has
you
a
should
basis.
provide it this way, because
I have the natural bit.
you
Yes,
have
I's and
you have there n
zero,
vectors
K.
which live in n different vector spaces. None of them lives in the tangent space to
Why is T?
0. Okay.
So all the FIs are function from
U to K.
No, this is
from U to K.
Right.
All the D's are function from
Tangent
TXX
space
to
X.
K. So they're all
Tangent space of K at 0.
T is 0.
they're all each of them is a function. It's derivative of the.
T0.
The FIs are functions from U to K.
Right.
So dFi at X is a function from Txx or Txu, whatever, to K. So it is an element of the domain. Xu doesn't matter. Okay? And, well, it is an exercise then for you to realize
Okay. Now
that this is actually a reformulation of this one when I took coordinates of 1. Okay, so actually I'm about to finish this chapter. I have two more things, which are immersion and submersion. It is very easy now to grasp, but it will be lengthy to formulate, so I'll not do it now, because we're done in 2 minutes. Not in 15 minutes, but I want to be there in 2 minutes. And so we'll meet next week, I think. Are there any other questions about that? So just pretty soon we'll finish the analytic geometric part. I said basically what I want to say, or I will say it in 1 hour. And then we relate this to algebraic geometry. Other local fields, or other things, as we discussed here, complete fields.